Yeah, I will do it. Okay. So do one thing. I have a recording now, and later on I will come back. Yeah. Just give me some time. Good evening. Good evening. Good evening, everyone. Just a moment. I was away from my desk. Let me change it. Okay. Fine. Let me share my screen. Okay. So we begin. So as usual, we are starting with the chapter on rotation. Right. Okay. So the problem reads finding the torque above the normal. Okay, an excellent problem which one needs to know, because conventionally there are two misconceptions I can say here. Conventionally, one learns that the normal force should always be drawn from the center of mass. I will show you that this is not correct every time. Okay, now towards it, before understanding the problem, let us look at this like this. Let us say I have an inclined plane, making an angle theta. I keep an object here. Now what will happen to the object? As you guess, the object will slide. Good. Now instead of this object, if I keep an object like this, the height is much larger than the width. Now what will happen? Do you think this will slide? No, this won't slide, right? This will topple down like this. Correct? Just bend like this. It's something like I have this case. If I keep it like this, and I keep it in a plane like this, it slides. It slides. Break this. Okay. On the other hand, instead of keeping it like this, if I keep it like this, if this was a flat base, then definitely, see, it falls down like this. Now it topples. Now the question is, why does it topple? Why doesn't it slide? The answer here is that here, the normal force is like this. Now, as it starts sliding, and if it is a rough plane, it's a rough plane. Now, what can happen is, this is what is the object. This is my normal plane, normal drawn to the plane. Now, as it drops, the normal will now shift like this. Why does it shift like that? Okay, if it has to topple like this, which point, with respect to which point will it topple? It will topple with respect to this point. I'm drawing this object here. It will topple with respect to this point. That means the normal should always start from the point where it is in contact, right? So therefore, it should topple from here, which means the normal reaction should come over here. Either it should come here or it should come here. Somewhere it should come, which means it is not going to pass through the center, right? As it is going to slide and it is about to topple, definitely because of friction, normal force will shift its position. Okay, I hope you are clear about it. Okay, now what it has to do with toppling? Okay, since normal force shifts over here, we have just learned that normal force only shifts. Okay, to topple, what do you mean by topple? It's nothing but a rotation. Okay, it may not be full rotation, but whatever is there, it's not straight like this. It's not straight sliding like this, but instead it is going to topple like this. It's going to rotate. How do I know rotate? Because this position, if I consider this tip of the finger, okay, it's describing an arc of a circle like this. So you can say that this tip is now making a circle like this. Okay, now I have given you sufficient background. Okay, we will see this after we look at the problem which is student encountered. Now the question is, a cubical block of mass m and 8 slides down a rough inclined plane, okay, of inclination theta with a uniform speed. Okay, fine. Find the torque of the normal force. The moment I talk about normal force, student did not consider this. Okay, so when I explained you all this, you thought, oh yes, It not only slides, there's a possibility it can topple like this. That's what you thought now. Okay, but if this is not explained, what will you think? You will always think, yeah, when the object is sliding like this, okay, why should it topple? Why should it rotate? Until and unless it is not a sphere, it will not rotate. So therefore, definitely we'll write, if this is not rotating, then torque equal to 0. Which torque? It's not the net torque is asking. See here, find the torque of the normal force. Read the question properly. Torque of the normal force here should be 0. That's what we think. Okay. So therefore, the answer given by a student is torque equal to 0 as it slides. Okay. Now, well, let us look at the correct solution. Now, what exactly happens? When the object is moving like this, then what can happen? This is my normal force. Which is a normal force? This is my normal. This should be the normal force if it is stationary. But when it is moving like this, there is a tendency that this object can topple. So normal force will shift over here. And there is a possibility that this surface might be like this. Might be like this. Might be like this. Which means what? If this is a inclined plane, this surface is slightly lifted upwards like this. Slightly lifted upwards like this. And most of the contact is here. Less contact is here. That's why you see normal force is shifting here. Okay. So it is not at this point. Now let us draw the free body diagram for this. So mg sin theta is acting like this, frictional force acting like this. mg is acting downwards, mg cos theta is acting downward, this side. Okay. Now what happens? Find the torque of the normal force. Now why do we get a torque? Because you see, above the center of mass, if I consider, this is normal force. Okay, normal force multiplied by the perpendicular distance between the center of mass. If I want to find a torque about this point, okay, this will now be equal to, the torque will now be like this, which means what? It will now try to topple it in this way. Now try to topple it like this. Now try to move it like this. Then you will say, hey, how is it possible here? It should always topple like this. Why is it possible like this? I agree with it. Okay. Why does it move like this? That we'll see. Okay. But before that, let us understand what's happening in the physics behind it. Okay. So now there is something like it is moving like this. Okay. The torque is now in this direction. Now, so that means this normal force should now see to it that it moves like this. It topples away from here. Now let us look at this one. Now the frictional force is in this direction. Mg sin theta is in this direction. If you look at this here, the torque of the normal force acting on it, and it is moving at uniform speed. See, it is moving at a uniform speed. What does it mean? It tells me that the frictional force is equal to the mg sin theta. Mg sin theta. Now what will happen to the torque due to this mg sin theta? The torque due to the mg sin theta, okay, will now be, what will happen? It will be like this. It will be like this over here. Which means you have one torque due to the normal force. Normal force acting like this. It is producing a torque like this. And this mg sin theta which is going like this, which has been pulling like this, it produces a torque like this. Now, these two torques will balance each other. You can say, this is your positive torque, this is your negative torque. Or maybe this is your positive torque, that's your negative, whichever way you want. But if these two torques are equal, then what can happen? The body will not rotate. Are you getting me? The body will not rotate. And that's what you observe also, right? You observe that when the body slides, it does not rotate. Why doesn't it rotate? It's because there are torques produced by the normal force and the mg force, but these two forces, these two torques balance each other, and as a result of this, the net torque is equal to 0. Okay, so it's not the torque due to the normal force. Now we need to compute it. I hope you got the concept now. Now let us compute the torque due to normal force. Torque due to normal force is n into x. This should now be equal to, okay, this is mg sin theta. And then, which is a point? This is my point. Now, what is this distance? According to you, it's given as a. This is edge is a. This whole thing is a. So this is a by 2. This is a by 2 now. So mg sin theta multiplied by a by 2. Why I have taken this? Because this is my start. This is my what do you call the reference point. So this should be equal to mg into a by 2. mg into sin theta into a by 2. So this should be mga sin theta divided by 2. This should be your answer for the torque experienced by the normal force. A torque produced by the normal force. I hope you have understood this concept. And if you have any more questions, you can always write back to me. I'll be happy to answer. Thank you, friends, for watching this video. And if you like, do share and subscribe to my channel for further updates. Thank you.